Okay, yeah. Welcome everybody. Welcome everyone to the 82nd meeting of New Directions in Group Theory and Triangulated Categories. Today our speaker is Tom Bachmann from the University of Mainz, and he'll be talking to us about p-adic homotopy theory and E-infinity coalgebras. I mean, if your name is pronounced Bachmann and not Bachmann, I'm sorry.
That's no worries. Well, thank you very much for the invitation. So I will try to share my screen and write on my tablet. And I was trying to do it like 1 minute ago and everything crashed. So I think I was crossed. I will share my screen. And now we can write something. That's a good start. This doesn't work. It does work. Okay, so hopefully now you can see what I'm writing. So I want to talk about E-infinity coalgebras and p-adic homotopy theory. And to begin with, I guess I wanted to say something about the coalgebra. Of course, like a lot of people know what the coalgebra is. Some don't. So if I take a symmetric monoidal category C, then
Tom,
yes.
we can't see you now. Is that intention? Is that?
I think there's no way around that. Unfortunately, my tablet is not strong enough. I'm sorry.
Okay, no problem.
Okay, so I have this, and then I can define a co-commutative coalgebra. And I mean, all my coalgebras are going to be co-commutative. So I will just say it once. Okay, coalgebra. It means the following thing. So this is an object C in my category, together with some structure. And so there's a very pedestrian thing, which I will say first. So together with maps from C to the unit in C. So this is called the co-unit map. And a map from C to C tensor C. This is called the co-multiplication map. Okay, and then you will ask that certain diagrams should commute. And this gives you a category of co-commutative coalgebras, and I will denote this by CC alg of C. Okay, a lot of C's, sorry about that. So that's the definition or the recollection. And the first remark that I need to make is that this is a very bad definition. Okay, and I guess the technical term is that it's a biased definition. So I'm using somehow this zero area operation of the co-unit and this binary operation, somehow co-operation of the co-multiplication. And I'm not taking into account the fact that I can also like have a threefold co-multiplication and so on and so forth. And so if you do this in infinity categories, you will find that this is not working well. But I mean, if you're aware of this problem, then you're also aware how to fix it. So
Tom.
Yes.
Would it be possible for you to increase the thickness of your lines?
For sure possible. How about, well, okay, how about this?
This is much better. This is much better.
Right.
Yes.
Let's go for that.
I had a comment in the chat that the bottom of your screen can't be seen. Maybe it's because the tablet is in the portrait mode.
Right. So maybe I do it like this.
Yeah, this is.
Now the bottom is here. Is that good?
Yeah, John, is it okay?
Okay,
I think this is much better. Yeah, I think this is much better. Sorry.
Okay. So as I said, this is unfortunately bad, but if you know what bad means, you know how to fix it. And let me also say that all this is saying is that a coalgebra is basically an algebra in the opposite category. And so this allows you to write a very quick definition of a coalgebra. Namely, you can just say that the co-commutative coalgebra in C is the same thing as a commutative algebra in C up. And then, okay, so you want the maps to still go in the correct direction, so you put another op on the outside. And well, if you know how to correctly define commutative algebras in infinity categories, then you can also use this definition for the co-commutative algebras, okay? And then it's not biased. Okay, and so the primary examples of coalgebras that I have been interested in lately is the following one, which is also very stupid, but well, sometimes stupid things turn into slightly less stupid things. And so this is the case where just C is Cartesian. Okay, so this just means that the tensor product is the usual product in the sense of category theory. And what then happens is that the forgetful functor down to C from co-commutative algebras, if you just forget the coalgebra structure, this is actually an equivalence. Okay, so the point is that what this is saying is that every object is a coalgebra in a unique way, i.e. every C in C is a coalgebra in a unique way. And this is very easy sort of to see explicitly, at least in the sort of lower levels of coherence, right? So for example, you want a co-unit and it should go from C to the unit in your category, okay? But by definition, the unit for the Cartesian product is just the final object. And of course, there's a unique map like this, right? And then you want the co-multiplication. This goes from C to C cross C, okay? So there can in principle be many maps, but I mean, it will be determined by what you do with the projection. You get a C here and you get a C here. And one of the axioms is going to be that this composite should be the identity and this composite should be the identity, which I guess expresses the co-unitality of the multiplication or something like that. And so then this map here is forced to be the diagonal and so on and so forth. So this is a very easy exercise. And so what's slightly interesting about this is that sometimes maybe you study some functor out of one category to a different category, and the source category happens to be Cartesian symmetric monoidal, and the target maybe is not. And then what will always happen is that if you apply your functor to any object, you end up with a coalgebra in the new category, and this will be some extra structure, which is often apparently useful to keep in mind. So this is the following example. Let X be a topological space, and F a field. And then what I can do is I can just look at singular homology with F coefficients. Okay, so this is plain old singular homology from like algebraic topology 1 course. So this is a graded F vector space. Singular homology. And by what I just described, this will in fact upgrade to a coalgebra. In graded F vector spaces. Right, and so the point is that this is the Küneth theorem, right? So that indeed by Küneth, I can look at this functor homology of something with coefficients in F, and it goes, let's say, from spaces to graded F vector spaces. This functor is now symmetric monoidal. And hence, what I observe is that top is the same thing as co-commutative coalgebras in topological spaces. And this is not the same thing here, but CC alg vect F graded like this. And there's an induced functor here just because this is my functor homology, right? And this is the same functor. And hence, this functor here has been canonically factorized through here. Okay, so I mean, this is basically like the fact that the cohomology is a ring always. That's something which maybe is usually explicitly taught in algebraic topology, and the fact that homology, at least with field coefficients, is is a coalgebra is basically the same thing. Maybe I write this as well. Compare. All right. And so all of this is just a prelude to somehow the following question, which I guess is a very natural one. Sort of, what is the difference between a space and its homology? Which, I mean, of course, I'm in no way insinuating to be the first person to ask this question at all. And so I want to make this a bit more precise, because at the beginning, obviously, they're not really in any way the same. A topological space is absolutely not the same thing as a graded vector space, even with a coalgebra structure. So we have to make it more strong and more precise. So I'll do this as follows. So the first step is that by a space, what I mean is a homotopy type. Okay, so this is a topological space up to homotopy. Really, what I'm getting at here is that there's some so-called infinity category of spaces. And that's where my spaces live. And so then what do I mean by homology? Of course, you already got the gist that maybe I use infinity categories every now and then. And so what I really mean is the chain complex of the homology. So I upgrade this to a chain complex up to chain homotopy. Okay, so this is just a singular chain complex of X with coefficients in F. And this will also live in some category, which is not a category of spaces. And I will denote this category by K of F. Okay, and this just means the infinity category of chain complexes. Over F. And so now with these preparations out of the way, the functor which I'm really interested in is somehow this functor. C lower star. It takes in a space, and I will always use these F coefficients. And it goes from the category of spaces to the category of chain complexes. And really, I mean, I want to somehow say something interesting about this functor. Okay, so basically the rest of my talk, I want to convince you that for various values of F, this one can say interesting things about this. And at the very end, I will report on like a small improvement of results in this direction, which I've recently established with Robert Burklund. So to get the sort of flavor of the kind of result that I want to talk about is, let's say I take K equals Z. Okay, so K is not Z is not a field. All right, but so I want to still make the following statement. I consider this functor C star with Z coefficients, and I will restrict it to simply connected spaces, okay? Greater than 1, of course. And where simply connected space, of course, means that pi 0 of X is star and pi 1 of X is also star. And now I go to chain complexes. And so this functor is not an equivalence, but this functor is conservative. Okay, so what this means is that i.e., if you have a map F from X to Y, and it looks like an isomorphism in homology, then this F thing was an equivalence. And so this is kind of good news. I mean, for one thing, this is helpful in practice, right? I mean, if you have some map of simply connected spaces, then it's maybe easier to compute homology on both sides and observe that it's an iso than it is to directly prove that it's a homotopy equivalence. But also by this sort of program, if I want to say what the difference is between space and the chain complex, then I mean, this is sort of getting closer, right? I'm clearly not forgetting just about everything because, for example, I can tell if two things are the same if I at least am giving a map between them. And so we can upgrade this even further. So there's this notion of a rational space. And so this will happen if basically if all the homotopy groups are uniquely divisible. Okay, one may prove that this is also equivalent, I think, to all the homology groups being uniquely divisible. And then we get into this territory of so-called rationalization or localization of spaces. So I don't want to treat this in detail, but certainly for every simply connected space, there exists a rationalization. Okay, so this is some map X from X to a different space, which I will denote by XQ. And so this will also be a simply connected space. And it will be a rational space. And in fact, on homotopy groups, we will just be rationalizing, right? So such that the homotopy groups of the rationalization of the space are given by the rationalization of the homotopy groups. Okay, so this leads into this classical subject of rational homotopy theory. Let me also point out that we have that the rational homology of X is the same as the rational homology of the rationalization. And then one can prove the following theorem, which I think is due to Quillen, certainly not in this language, but at the very least in spirit, which is the following, is that if you start with a rational space, okay, so this means rational spaces, and then you do homology, okay? So let's say I do my chain complex, singular chain complex with rational coefficients, and out I get, of course, a rational chain complex. But as I said before, because this source category here is Cartesian symmetric monoidal, everything is automatically a coalgebra. And so in fact, I can land in co-commutative coalgebras in rational spaces, okay? And what happens is that this canonical functor is actually fully faithful. Okay, and so I mean, that is the sort of answer that I would like to give to the question, what's the difference between a space and its homology? So for example, if you take a rational space, and if you remember that the homology is in fact the coalgebra, then there basically isn't a difference, right? Everything you might want to know about the space, you already know if you know the homology. If you know it in this sense here, which is of course a lot of structure. All right. So to recap what has happened here, I want to point out that this, in some sense, I mean, I can view this as several statements happening at once. The first is that if I take just rational homology from, let's say, simply connected spaces so that we have a good chance, and then we go to rational chain complexes, this by itself is not even conservative. Okay, so I have no chance to reconstruct a general space from the rational homology. That's just not plausible. But what I can do is I can replace every space by somehow a better space, in this case, the rationalization. And then the functor does become conservative, okay? But it becomes conservative on this subcategory this subcategory, in fact, it is uniquely determined by this functor here, right? So if I look at all the maps which get inverted by this functor, they form a so-called strongly saturated collection of maps in simply connected spaces. And then by the theory of localization, one can always find the universal space somehow or under a given space with respect to this family of maps. And this is how these rational spaces arise. And then what is also true is that the functor, the induced functor, like this, is not an equivalence, of course, but so what happens is that this functor, it has a right adjoint, okay? This is my C star. This has a right adjoint. And whenever you have this kind of adjunctions, the category theorists have observed that when you apply the left adjoint, i.e. this one, to an object, you get extra structure on the resulting chain complex, okay? And this extra structure is encoded in something called a comonad, and that's basically just the composition of these two functors. So this functor is what's called comonadic, or close to that, i.e. there's a right adjoint R, and then we obtain a comonad, C. It goes from rational chain complexes to rational chain complexes, and that's given by C star R. Okay, this endofunctor here is what's called a comonad. And the induced functor from rational spaces to comodules over this comonad, this is fully faithful. Okay, and then I could view this as a third part of the theorem, which is that this particular comonad describes co-commutative coalgebra. Okay, and so the reason that I write it like this is that I want to make clear that this is a very general thing which you can do. Whenever you have a left adjoint functor, you can say, how can I approximate or understand the objects in the source in terms of objects in the target? And you can always say, well, at the very least, I have to localize the source at all the maps which get inverted. And then I get coalgebras, I get a comonad on the target, and I can factor it through comodules. And in some sense, the best thing which could possibly happen is that the functor to comodules is fully faithful. And if that is true, then you have to understand what this comonad is, and then maybe you get a good understanding. But each of these steps can somehow break down. And so the real thing that I want to talk about is that what happens if instead of using rational coefficients, I use FP coefficients. Okay, so then I will run my program. Okay, and so the first thing is that I have to give some name to the kinds of maps which get inverted. So these are called the FP equivalences. If the homology of F with FP coefficients is an iso. And then you can show that this is, again, one of these strongly saturated classes. And so there's an associated localization. And I will denote it by X maps to X P completed. Okay. And so now that's all well and good. It exists for abstract reasons, but so it can be described in good cases. So so if X is simply connected and all homotopy groups are finitely generated, then it turns out this will just P-complete the homotopy groups. Then the homotopy groups of X P-completed are given by the P-completion of the homotopy group. So there's something more. There's many more general things which can be said. Instead of simply connected, you can talk about so-called nilpotent object spaces, and I don't want to explain what that means. And instead of finitely generated, you can basically have no assumptions, and then you need to use something called the derived completion, which is a bit more complicated. But so one can understand this, and this is due to of my work of, I suspect, many authors, but like the canonical book about this is due to Bausfield and Kahn. So this is how I know these things. Anyway, so I get this category of simply connected and P-complete spaces. And more generally, I could use nilpotent spaces. But simply connected implies nilpotent. And for the purposes of this talk, I guess I will go with this. And then if you read this Bausfield-Kahn book carefully, you can see that they've helped us a lot with trying to understand this program, right? And in fact, what they prove is that this functor is monadic. So they show that this functor take the chain complex with FP coefficients, and it goes from P-complete spaces now to chain complexes over FP. This is comonadic. Well, they don't quite use this language, but I mean, what they say is that if you start with one of these P-complete simply connected, or rather P-complete nilpotent spaces, and you use something called a triple or co-triple resolution, then you get back this space. And that's essentially equivalent to this comonadicity. And so if you think back to my explanation before, how can you understand this kind of functor? Well, you first have to invert the correct maps. Then you have to prove it's comonadic, and then you have to figure out what the monad is. And so that's the obvious question that remains. What is the comonad? And somehow this is somewhat difficult, it turns out. And there's a key insight, which, as far as I know, is due to Mandell. And the insight is that instead of using FP coefficients, you could use FP bar coefficients, let's say. Lewis C star of blank with FP bar instead. Okay, so that answers a strictly different question, but it seems also interesting. So the first thing to observe is that you get the same localization, right? And the reason is that the homology of X with FP bar coefficients, that's just the same thing as the homology of X with FP coefficients, scalar extended to FP bar. Okay, so that's true because FP bar is flat over FP. And so you deduce that this map here is an isomorphism if and only if it is here. So I guess I'm now using that FP bar is faithfully flat over FP, but it's still not a particularly deep fact. And what Mandell has figured out is that in this case, the comonad is easier to describe. And so in fact, what he proves, and okay, so I'm going to write something. And what I claim that he proves is that you look at this functor from simply connected p-complete p-finite spaces to co-commutative coalgebras in chain complexes over FP bar. This functor is fully faithful. Okay, so I should explain what this finite here means. And the finiteness condition is just that the FP homology should be finite dimensional in every degree. And of course, he did not prove something about simply connected spaces, but rather he put nilpotent spaces. Anyway, and so also the other thing is that he for sure didn't write about coalgebras. Okay, so he wrote something about E-infinity algebras, but because of the finiteness assumption, in his case, you can somehow dualize algebras and coalgebras, and you can talk about either of them at the same. It doesn't make a difference. So out of Mandell's result, you can deduce this with fairly little work, and you can also go in the other direction. And so now I'm ready to explain what Robert and I did, which is now very easy, which is basically just that we remove this finiteness assumption. Okay, so the same is true for simply connected p-complete, and if again you can use nilpotent spaces instead. Okay, so I mean, I think this is an extremely natural question, right? So after Mandell proved this with some strange seeming finiteness assumption, which I mean, you can explain because he does cohomology. And of course, if you do cohomology, you dualize somehow, you want some sort of finiteness. But I think it's a very obvious question to ask if you can get rid of this by going to coalgebras instead. And so we thought surely someone must have proved this, but we asked a lot of people and we couldn't find anyone who told me that it's been done, and we figured out some proof. So we thought we would write it up and explain it. Okay, so maybe now is not a bad time for me to ask if there are any questions so far. Okay, well, I can't see anything, but I'm guessing this is a no. So, right, so first of all, let me describe sort of how Mandell's argument goes. And so what he observes is that you can compute the homology of Eilenberg-MacLane spaces. Of course, this has been known for a long time. And you can relate it, well, he related the cohomology of Eilenberg-MacLane spaces to free E-infinity algebra. And if you dualize his description, you can relate it to co-free coalgebras. So he says that he proves that there is a pullback square of the following form. You look at the co-free coalgebra on FP bar vector space of dimension 1 in degree n. And you put the co-free coalgebra on FP bar vector space in degree n. And there's some mysterious map here, which is called the Artin-Schreier map, or Frobenius -1. And there's a map from the unit object into here. And you look at the homology of an Eilenberg-MacLane space. and with FP bar coefficients like this. And it turns out that you can form a pullback square like this. And this will be, well, you can form a commutative square like this, and it will be a pullback square in the category of co-commutative coalgebra. So I guess I should explain some things here. So what is this C functor? The C functor is called the co-free coalgebra. And so it's the right adjoint of the forgetful functor. Okay, and so knowing this, at least you can figure out what this map does here, right? So if you want to map into a co-free coalgebra, you just have to give a map into the underlying vector space somehow. And so what this says is that you should produce a canonical class in the homology of the Eilenberg-MacLane space in degree n. And of course you can, right? So there's a tautological class there, which you can use to make your map. And what this is saying is that somehow if you compose this with the strange Frobenius -1 map, then more or less you get 0. And this seems to be a property that the homology enjoys. And once you have this, you can build this commutative square, and you can ask if it's a pullback. And so dually, you can talk about cohomology. And then again, this is saying that the cohomology has a canonical class which you can hit. And then what this pullback, what this commutativity condition says is that Q0 in cohomology acts as the identity. And so here's somehow a dual statement about homology. And so why does this help you? Okay, so let's say you can prove that, right? It's a fun observation. You can compute everything on both sides, and it turns out to be the same. At least if you do it in E-infinity rings, you can compute everything. And so now what you want to do is you want to know that this functor is fully faithful. So let's better do maps out of the unit object. Okay, so we can do the following. Then we find that maps, let's say in co-commutative coalgebras, K of FP bar, like this, from the unit object to the homology. Okay, so if everything works as advertised, this should give me back the Eilenberg-MacLane space. And so this will sit in a pullback square. Down here, I get maps to FP bar, so there's nothing here. This should be FP bar. And here you get maps of co-commutative coalgebras from FP bar into my co-free coalgebra on FP bar n. And here you get the same thing, Frobenius -1 maps FP bar into co-free coalgebra on FP bar n. So you get this kind of thing. And so you know, as I said, you know what this is, right? Because you know how to map into a co-free coalgebra. And what you get is just the thing which you had before. So you just get the infinite loop space of FP bar in degree n, which is also called K FP bar n. And you get the same thing here. And then there's some mysterious map here, which is somehow Frobenius -1. And then what you can imagine is that, well, this K of FP bar n, it basically has a FP bar homotopy group in degree n and nothing else. And so you look at Frobenius -1 on this, and well, it's surjective because FP bar is algebraically closed, and the kernel is FP. And so you find that this pullback here, in fact, does give you back FP. And so what this sort of tells you is that the fully faithfulness seems to work, at least in the case where X is an Eilenberg-MacLane space. Okay, and then, I mean, you can imagine that if you have some kind of space which is somehow sufficiently finite, then you can maybe build it up out of Eilenberg-MacLane spaces, maybe for Fpn, and maybe you also need to deal with Zp, but you can sort of imagine that this is a hard step, and then getting to all the spaces is much easier, or all the finite spaces is much easier in some sense. And so what we do is that, so I should say, right, so you can get to sufficiently finite spaces. For example, you can start with Fpn, and that everything will be compatible with finite products, so you can get Fp's two-dimensional vector space or three-dimensional vector space. But it's not at all obvious how you can get an infinite dimensional vector space. And this is basically the main thing that we do. So our contribution is we do the same thing, and we do it for an arbitrary Fp vector space V. Okay, in particular, an infinite dimensional one is what's complicated. And well, I mean, we look at the Eilenberg-MacLane space KVN. And so now you say, well, okay, Mandell did the one-dimensional case. How much harder can the other one be? What's going on? And the point is that somehow this is not so easy. So let me say something about why this is difficult. And so the main reason for this is that I have been writing things about coalgebras and pretending like I can work with coalgebras for this talk so far. But this is not necessarily a lie, but certainly sweeping a lot of things under the rug. So let me say coalgebra. One big problem is that coalgebras are not nice. Okay, so for example, it's not obvious that the category of coalgebras is presentable. It's not obvious that the co-free coalgebra functor exists. Okay, so now if this would be my only complaints, then I mean, I would again not I would be whining for no reason. So I mean, this is known to be okay. I think in elliptic 2 or something, Jacob Lurie proves that the category is presentable and that the co-free coalgebra functor does exist. But at the same time, there are still other problems. Okay, so for example, there's no formula for the co-free coalgebra. I trust that you know the formula for the free E infinity ring, right? So it's the direct sum of x to the tensor n, and then you take homotopy orbits for the symmetric group action. So in particular, you could guess something like co-free coalgebra on x is going to be, well, everything is dual, right? So I take an infinite product of n greater than or equal to 0, x to the tensor n, and then the dual of homotopy orbits is homotopy fixed points. Okay, and this doesn't work in general. And another related fact is that if you take the unit coalgebra, this is not compact. Okay, and I mean, the reason why that is relevant is that, of course, you can write a general infinite dimensional FP vector space as a filtered co-limit of finite dimensional ones. And I told you that somehow you can deal with finite dimensional spaces. And so if the unit was compact, then you can have some kind of easy continuity argument to reduce from the finite dimensional case to the infinite dimensional case. But again, no such luck. And so what's our main idea? the main idea is that in some sense, all the problems come from the fact that co-shifted limits do not commute with tensor products. Right, so for example, if you look at this formula here, why does this work? And I mean, if you look in higher algebra where they prove this formula, then you will find somewhere that the tensor product should preserve co-filtered limits, and it should preserve, the tensor product should preserve shifted co-limits, and that just won't work. And it's also pretty easy to imagine, because I mean, how do you even make this kind of expression here into a coalgebra? I mean, there's some infinite product which you somehow have to deal with, and you can't commute it with a tensor product, and it just doesn't work. And as far as I can tell, basically all the problems with coalgebras come from this. And so there's a very mathematician-y, I guess, way of going around this, which is to say, all right, let's replace our category by something where it does work. And so the category which you can use is you use pro objects. Or I say pro object in C in general. Okay, so then, I mean, in some sense, all your problems go away, right? So for example, what I want to say, yeah, so if I mean, for example, this formula for the co-free coalgebra is correct, right? So example, if X is in C, and if I write Cx in pro of C for the corresponding pro object, so constant pro object, then you can do the co-free coalgebra on Cx, and this is now the product of the so you get something like this. And many other good things also happen. And so what you find is that if you were just allowed to work in pro objects, then you could basically just compute to your heart's content. And so to some extent, the main theorem is something like the following. Is that if I take some finite dimensional, some infinite dimensional FP vector space, then I look at the co-free coalgebra on the constant thing FP bar tensor V, and I place it in degree n. Then I do the co-free coalgebra again. And now it turns out that you can again put a Frobenius map here. Okay, and then there's also an FP bar, which I can put here. And then there's going to be some pullback, which I'm just going to call E here. And so this is going to be a co-commutative coalgebra in pro objects in chain complexes over FP bar. Okay, and this guy for sure is accessible to computation. Okay, so you can use your usual Tor spectral sequences, I guess co-Tor spectral sequences or whatever. I guess you have to make them continuous. And so you get out some guy. And the surprising fact is that this E thing is essentially constant. Or it's pro constant, is constant up to pro truncation. Right, which means that this, if you look at the pro object, if the tau less than or equal to IE is pro isomorphic to some pro object of the form tau less than or equal to I E prime, where E prime is some constant guy. like this. And so why does this help? The reason why this helps is also the following warning, is that if you start with the co-commutative coalgebras in pro objects, you can forget down to pro objects. And you have pro just k of fp bar. And here there's a functor, which is basically take the limit, okay? And you can also start with coalgebras in k of fp bar, forgetful functor here. And here again, there's a functor which is somehow take the limit. And the main point is this is the right adjoint to the constant, right? So taking the limit is right adjoint to the constant object. And here also there's a constant object. Maybe this is the limit in co-commutative coalgebras. And the warning is that this diagram does not commute in general, okay? But it will commute on the subcategory of constant objects. And so I can summarize our strategy as follows, right? So you make this commutative square here. Where is it? Here. Okay, so you make this big commutative square, except instead of taking FP, you take some V here, and you take some V here, and you take some V here. And you're trying to prove that this is a pullback square. And you don't know how to do it because you don't know what these things here are. And you don't know how to compute this pullback. And what you do instead is, all right, you do the computation in pro objects, and there you can compute to your heart's content, and you find that you get the answer that you expect, okay? So you find that the pullback of this thing is indeed this thing. And in fact, it's constant. And then what you learn is that, okay, because this limit functor here commutes with the forgetful functor on constant objects, you've now learned that the previous computation, which was impossible to do, right? Because you didn't know what a co-free coalgebra was, and you didn't know how to compute the pullbacks of coalgebras, somehow the answer is still the answer, which is the same as in the pro objects case. And so we have sidestepped this problem. Okay, so that's my summary of what we do and how we do it. I guess I'm finishing 5 minutes early. I'm sorry.
You can, yeah. Oh, sorry, did you say you're finishing now?
Yeah, sorry. I said I'm finishing 5 minutes early.
Okay. Yeah, okay. Let's all unmute ourselves and give Tom a round of applause. If you have any questions, you can ask the speaker now. I'm not sure, but it might be helpful, well, depending on the questions, to keep the writing
right. So I thought I would get it up again, but I can also open it right now if you want me to.
Okay, let's see if there are any questions.
Could I ask, please? I don't actually know what pro objects are. I know what pro functors are. Do they have anything to do with that?
Well, I don't know what pro functors are, but I can show you what pro objects are. That's I think something I can define. So there's two things which I can do. The first, which is not entirely a joke, is that pro objects in C is the same as int objects in C op. Then you op it again, okay? So lots of people know about int objects. Maybe they don't know about pro objects. The other thing is also that I'm basically pro objects in C. That's co-filtered, formal co-filtered diagrams, right? It's something like x0, x1, x2, Okay, this would be one kind of diagram, but I mean, this is now indexed on 0, 1, but more generally, this is objects of the form x lambda, x lambda, lambda in I, where I is some co-filtered category. Yeah, so it's the category of formal co-filtered diagrams in C, and so it's purely somehow a diagrammatic type of reasoning. Is that a helpful answer?
Yes, but so the diagram is actually a chain, finite at one end and going on.
No. It's any co-filtered category. I mean, I usually think of 0, 1, 2, and so on, but it could be bigger. It could have some branches. Somehow the indexing category is not relevant. You're allowed to replace it by, for example, a co-final subcategory, this sort of thing.
So it's a category where the objects are such diagrams.
Yes,
yeah.
But the shape is not fixed.
Yeah, okay. And with the end objects, which I didn't know what those are either, but presumably, as you said, it's the opposite construction. Yes. Yeah. Okay.
Thank you. Filtered diagrams.
Thank you.
Okay. Thank you, Peter. Any more questions or comments?
Is there a, excuse me, result with FP coefficients?
I think it's believed that there's a result with FP coefficients. That is, I mean, you somehow have to take into account something called Tate diagonals, which I suspect you know more about than me. So it's somehow dual to this thing that Alan Yuan did. We have not worked that out, or nor are we, I think, intending to. Maybe Alan actually intends to do this. But it's more complicated, right? So the comonad is strictly more difficult if you go into FP modules.
Okay, thanks.
Sure.
Thank you, Jay. Any more questions?
Hi. Could you explain how you see that the unit is not compact?
I don't think I can explain that. It's not obvious to me. There's a remark in some paper of Jacobs, which says that this isn't the case, and I think gives an example. And yeah, so as a meta answer is if it was compact, then our result was basically trivial. Yeah, so I cannot exactly see this. I'm sorry. It's also surprising. I guess you're asking this because in the zero truncated version, this is of course false. It's somehow an important theorem. But apparently, as soon as you allow bigger, I mean, as you allow non-zero truncated objects, apparently this becomes false.
Thanks.
Thank you, Georgios. Any more questions? Right. So whose paper has this comment about the non-compactness of the unit?
I think it's also in elliptic 2, but I would have to look it up again.
Okay. Is it in a language that we might find familiar?
I'm pretty sure it says something like the unit is not compact in this and that category.
Okay, yeah. Okay, do we have any more questions for Tom? If not, let's thank our speaker once again. So this was our last talk before the Christmas break. We will be back in the new year with Srikanta Iyengar. Bye-bye.